And then in the daytime, we don't need it because we need to be awake. Okay, we do understand that part of it. It also seems to be involved in this idea of having a biological clock. May have something to do, again, with the onset of puberty and the onset of menopause, but nobody can figure out how and when and where it has its effects. This hormone, we know a lot more about it in a lot of other animals. It's the hormone that regulates the guys who do the flying south for the winter and the estivating, the hibernating, okay? It's a master controller, and it seems to work by interpretation of light and dark, okay? How do birds know it's time to fly south for the winter? They used to think it was their food supply, that the changing food would actually make them say, oops, the seeds are changing, so we have to move. It's not that. It has to do with the length of the night, how long the nights are. As the nights just barely start to get a little bit longer, they know it's time to go. So, and it has to do with the pineal sensing images or light. Well, actually, it works while you're asleep. We have input through the optic nerve that we're not aware of, and it signals into the pineal. And it controls the manufacture of this bizarre little hormone in us and a lot of other things. So things happen at night that you're not even aware of. Question?
If somebody was blind, would that affect them in their daily rhythm?
If there is an optic nerve, if the optic nerves are working, then you would have the same kind of response as anybody else. However, there would be problems with that if you're actually completely functionally blind and don't get any light information. Hang on a second.
Also, people that work at night.
Okay. What happens is, okay, for people who work the night shift, and a lot of you do already or will at some point, okay, and you know, if you completely shift your schedule so that every day you are consistent, that you're up at night and you're asleep in the day, it's hard to live like that because the rest of the world goes on without you. So what most people end up doing is the nights that you have to work late, or the nights you work, you stay up and you work, and then you try to catch up sleep here and there, and so you're constantly asleep in the day, asleep at night, asleep in the day, and it's mixed and it's havoc, okay? Very hard on the rest of your body, okay? Because we are not nocturnal creatures. We're really meant to sleep at night. Okay, and if you completely shift everything so that you do opposite for 7 days a week, for years at a time, you can shift your hormones completely out of whack a little bit, but it's still not exactly, you'll still never feel exactly the same as a person who sleeps at night and is up in the day. And usually what happens is, and I kind of lived through this because when I was a kid, my mom worked, she was an RN for the VA, and she worked 12 to 8. So she worked midnight to 8 a.m. for about 25 years, okay? And she would say that she had a regular pattern and rhythm, okay? About 1:30 in the morning, she'd get kind of tired, and then by, 4 o'clock in the morning, when certain things would happen on her shift, she would be wide awake. She's 86 now, and she's been retired for 20 years. And 4 o'clock in the morning, she still wakes up. She's completely awake for about an hour. The changes in her cycles were permanent. It was so many years of a pattern that even though she sleeps now at night, it's never the same. You mess yourself up, honestly. And I hate to tell you that, but it's tough. Okay? Question, Jennifer.
Well, it was just about what she was saying. There were some studies done that even if you covered your eyes and there was no light on skin,
Right.
that could affect that. I don't know how that came out. I don't know if that was proven to be true or not. Because that was back in the 90s. But
Yeah. See, even the blind, there has to be something else going on that we don't understand. Okay, there definitely has to be, because if you compare melatonin levels of somebody who cannot see, it still ends up being like about the same as somebody who can. So, like I said, we're having a little psychedelic event back there. Go ahead. Morse code. Someone's trying to signal us from above. There's a light back there flashing. Yeah. Yeah, what? Me, I'm seeing flashing lights.
I hope you don't get seizures.
Yeah, really did. Yeah, don't let me look. No epileptics, right, please.
Turn the- oh,
Let's see, are we trained enough?
unscrew it or
No.
something. There you go.
Put it at rest. Make a mean mess. Okay. Next, we've got a set of organs, a set of endocrine glands, endocrine cells in places where we do other jobs, okay? Remember how in the beginning we said some endocrine organs are, they just do endocrine jobs, and we also have some endocrine tissue in other organs. Well, that's what this part is about. Our first organ that has dual function is going to be the pancreas. It has digestive function, as we'll learn about. It's going to make a bunch of stuff that gets added into food to help break it down. But it also has endocrine function in that it makes two really important hormones, okay? There are specific regions inside the pancreas that are called the islets of Langerhans. They look like little islands, and so that's why they call them islets. Little groups of cells, okay? And in these islets is where we make these two hormones. And of the islets, we actually have two different kinds of cells. One set of cells called A cells that make glucagon, the other set of cells called B cells or alpha cells and beta cells, and they make insulin. Okay, now these two hormones are antagonistic. Okay, they do opposite things. Glucagon's job is to increase blood sugar levels, so it's made when blood sugar level is low. And insulin's job is to reduce blood sugar levels, so it's made when blood sugar level is high, and we'll see how this works a little bit. Okay, we'll talk about each one just a little bit more. Okay, and what they do. Okay, glucagon's job again is to get blood sugar level up. So when blood sugar drops, we make this hormone. And what this hormone is going to do is it's going to work at kind of three different levels. Okay, it increases the ability of the liver to break up glycogen, okay? The process is called glycogenolysis, but it's we're breaking up glycogen, and the glycogen that we're breaking up is stored in the liver, okay? One molecule of glucagon can get us to actually free up 100 million molecules of glucose. Okay, it's actually that effective. So, and again, the first way it works is we store excess glucose in the liver. If we have sugar in the liver, in the blood, we're going to sequester some of it in the liver while it's on its way through and grab it and package it up in glycogen, because it's not doing any harm. And then when we need some of that sugar, we make a little bit of glucagon, very little bit. It acts on the liver and we break down glycogen into glucose, and then if we jump right down here, okay, we end up increasing the release of the molecules of glucose that got freed up from our glycogen from the liver. So we not only break it down, but we make sure that it gets out in the blood. Okay, and then the other thing here is that we can also increase the making of glucose from other sources, like from proteins if necessary, or from fats, okay, from other molecules, like even from lactic acid, okay? If you remember, lactic acid are left over from skeletal muscle. If we don't have oxygen around to make ATP, we end up with a byproduct. We only make a little bit ATP, and we have this leftover of lactic acid. Glucagon can get the liver to take that lactic acid and turn it back into glucose. Okay, so we kind of we even scavenge that. Okay, so and I have here on my list, trying to read my notes.